right, are we all in? Everybody out there who wants anybody still out there? No, maybe not. Okay, so today your lectures are going to be on tropical cyclones. The reasoning being that the Mediterranean cyclone is said to have features that are tropical cyclone-like, and so we thought it'd be a good idea to have a lecture on what are tropical cyclones like. So at least you'll have one pole to compare against when you're thinking about MedCyclones. So this is purely on tropical cyclones. This lecture, I have to confess, about a month ago I was running out of time, and I worked hard on putting together the second lecture, the theoretical lecture, and I thought, well, I'll see if I can get the observational material together. But I was at the Tropical Cyclone Conference in New Orleans in May, and my good friend Kerry Manuel was there, and I asked him, Kerry, do you happen to have a introductory lecture on hurricane observations? And he said, sure. So within minutes it was sent to me. And so this is an edited version, because there's a lot of things in here that aren't pertinent to the dynamics of tropical cyclones. So anyway, this is based on the Divine Wind, Kerry's book. That's in the Oxford University Press. So let's start with the definition. So here's the official definition from the NOAA National Hurricane Center. A tropical cyclone is a warm core, non-frontal, synoptic scale cyclone originating over tropical or subtropical waters with organized deep convection and a closed surface wind circulation about a well-defined center. Once formed, a tropical cyclone is maintained by the extraction of heat energy from the ocean at high temperature and heat export at low temperature of the upper troposphere. In this, they differ from extratropical cyclones, which derive their energy from horizontal temperature contrasts in the atmosphere, and those are baroclinic effects. A hurricane definition used, again, by the weather services in the U.S. A tropical cyclone with a 1 minute average winds of at 10 meter altitude in excess of 32 meters per second, occurring over the North Atlantic or East and North Pacific. The advent of reconnaissance aircraft and radar in the 1940s and of satellites in the 1960s gave scientists the means to determine the detailed structure and evolution of hurricanes. Today, almost everything we know about hurricanes is based on observations by aircraft, radar, and satellites. This satellite image shows Hurricane Floyd, 1999, just off the east coast of Florida. This image has been digitally enhanced to lend a three-dimensional perspective. The swirling mass of clouds is about 300 kilometers across. Floyd's eye is about 50 kilometers in diameter. Surrounding the eye is a deep ring of thick cloud called the eye wall. A thin veil of very high cloud covers most of the swirling mass of thicker clouds. These are made up of tiny ice crystals, a veil of cirrus. Underneath it, and thus invisible from above, are several spiral-shaped bands of deep, thick cumulonimbus clouds interspersed between relatively clear skies. These spiral bands produce heavy rains and gusty winds well outside the eye wall of a hurricane, where the strongest winds are found. Okay, and I should say, just interrupt any time you got a question about something. Okay, if something's not clear, if you want to know what a cumulonimbus cloud is or something like that, raise your hand and we'll go through it. Okay, so this is a picture from the space shuttle taken in 2010. This is Hurricane Igor. The storm was a Category 4 hurricane on the Saffir-Simpson scale of intensity. At the time of the image, it was centered about 18 north, 52 west, and slowly moving west-northwest at 11 kilometers per hour. According to the U.S. National Hurricane Center, maximum sustained winds of 213 kilometers per hour it had with gusts of 259 kilometers per hour. This is Hurricane Amelia, again from the Space Shuttle, Columbia, 1994. At this time, Amelia had maximum sustained winds of 155 miles an hour. Looking at the eye from above is like staring down the middle of a bathtub whirlpool. I'm going to show you a picture of a bathtub whirlpool in the second lecture because it helps to understand the eye. Except that the boundaries are made of cloud, and the funnel comes to an abrupt end at the sea surface. The eye wall is visible as a stadium of thick white clouds surrounding the eye. This is where the strongest winds and heaviest rains are found. Unlike the bathtub whirlpool, the air inside the eye wall is going up and not down as it swirls around the eye. There are spiral striations along the inner edge of the eye wall and two big swirling eddies, in this particular case, in the low clouds at the base of the eye wall. No mere photograph can do justice to the sensation of being inside the eye of a hurricane. You have to imagine a Roman Colosseum 20 miles wide and 10 miles high, with a cascade of ice crystals falling along the Colosseum's blinding white walls. Okay, so now we're getting to some NOAA reconnaissance aircraft, and this is kind of the view from inside the stadium. So now we're inside the eye wall with these reconnaissance and looking at pictures of this. You see the sloping wall here, and then this is the subsidence region and low clouds in the middle. Now, however impressive a hurricane's visual appearance, it is the instruments aboard the satellites and aircraft that reveal the essence of a hurricane structure and inner workings. In the early days of aircraft reconnaissance, the crew estimated wind speeds by looking down and noting how rough the sea surface appeared. Today, a sophisticated array of instruments automatically collects large quantities of high-quality data, which are taken back to laboratories and analyzed. And here's a few more pictures from inside the eye. This is Hurricane Katrina, 2005. I think another one of Katrina, and yet another one, and another one looking down deep into the hole of the eye. This is what when you can see the sea surface. Here's what it looks like. There's a lot of little swirling eddies in here, looking down low. So these aircraft have a radar on them, and this is a picture of a slice through the radar. Slice through the hurricane, and you'll notice the main features. There's here's the eye, and the eye is in the middle. Then there's the eye wall, more or less continuous echo around, and then there are spiral rain bands farther out. That's a low-level cut, and a vertical horizontal section of something like this. So again, here's the walls of the stadium going up like this. This is the rain. So basically, this is telling you that there's rain and decreasing as we go up higher, up to 10 or 12 kilometers. It's gone. Here's a picture of one of the early pictures based on a reconnaissance aircraft of the isotachs. That's to give you an idea of the distribution of winds in a hurricane. These are knots divided by 2 to get meters per second, and nautical miles, and I think you multiply by 2 to get kilometers. So anyway, yeah, so it's a very tight, in this particular case, very tight gradient from near zero winds in the center to here 130 knots and at the radius of maximum wind. So here's a reconstruction of the tangential wind. I'm going to alternatively refer to it as azimuthal, because it's in the direction in cylindrical coordinates. The direction going around is called the azimuthal direction or tangential wind. Both of these are used very commonly. So this is a composite view of the distribution of wind speed in a typical hurricane based on measurements made from research aircraft. In this image, and the two that follow, the center of the hurricane is in the center of the panel, and the cutaway extends outward about 200 kilometers, and the upward about 18 kilometers. The satellite image of the top of the storm has been superimposed. The image shows that the speed of the wind going counterclockwise around the center of the storm. The black dashed lines show the altitudes at which the aircraft were flying. If you can see, those are kind of faint. The darkest shade of blue indicates the lightest winds, each less than 5 meters per second up here. Each successive color represents an increment of 5 meters per second, reaching a maximum here of 65 meters per second in this picture. Okay, so this image shows a composite view of the distribution of updraft, vertical velocity, in a typical hurricane based on a computer model calculation. The yellow and orange represent a strong upward motion in the eye wall. Although it is too weak to be seen in the figure, there is a downward motion in the eye itself, down in here. Strongest right next to the eye wall, and also a broad region outside the eye wall of updraft. But since this figure is made by a computer model, let's see. Since this figure is made by averaging the air motion along the circles centered at the storm, the strong updrafts associated with the spiral rain bands are missed. Okay, so this is the axisymmetric version of that 3D image that I showed. So there's averaging around circles, and almost all the theory I'm going to talk about in the next lecture is for the axisymmetric tropical cyclone. And finally, again from the computer model, I think it was my computer model. I don't know for sure though, or our computer model. Yeah, and this is the radial wind. The radial is that you see very strong inflow in the boundary layer. Oops. Indicated by the orange lines, and then outflow at high levels. Okay, so the air comes in, spins, goes out, spins down, and this image shows a composite view of the distribution of temperature in a typical hurricane. This actually shows the difference between the temperature at any point and the temperature at the same altitude far away from the storm. The lightest shade of blue shows no temperature difference, while bright yellow shows air that is more than 16 degrees Celsius warmer than its distant environment. Each shade represents an increment of 1 degree C. Hurricanes are very hot in their centers, especially near the tops. This great warmth is one consequence of the enormous amount of heat sucked out of the ocean by the storm. On the other hand, there is very little change in temperature as you move in towards the eye along the surface. Nearly constant, nearly isothermal conditions along the surface. And distributions of temperature and wind in a hurricane are related to each other. Look carefully at the images in this slide and the slide that shows the wind speed. Notice that the rate at which the wind decreases upward is proportional to the rate at which the temperature decreases outward. This relationship is fundamental to rotating fluid flows and is called the thermal wind relation. So the comparison here is between this one. So this is the wind decreasing, the tangential wind decreasing with height corresponds to the temperature perturbation decreasing outward. And it's very fundamental, and it's going to play a central role in explanations of tropical cyclone that I'm going to give in the second lecture. So it's basically the same as what you might have learned in your dynamics courses and geophysical fluid dynamics, where the Coriolis force is the source of rotation. Okay, here's another very important quantity, the equivalent potential temperature. And this is a hallmark of tropical storms to have an equivalent potential temperature that looks like this, where it's large in the middle, and of course large as you go into the stratosphere. And one imagines then, based on those computer models and experience, that the flow is coming in through the boundary layer, gaining equivalent potential temperature, rising up, conserving its potential temperature, and riding outward, conserving its potential temperature. The angular momentum, well, again, which will be a critical quantity that we're going to use in our theorizing, is, again, where the flow comes in, it's losing angular momentum here, and then conserving it as it goes up and out. And this basic picture of the hurricane using the conserved quantities, the otherwise conserved quantities in the interior of angular momentum and moist entropy will be very useful in formulating a theory for the winds of a tropical cyclone. Okay, a little bit about the climatology. So they tend to these are cyclone tracks, and basically they form. This is the equator, 30 degrees north here. So they tend to form in the lower subtropics, and as they move, they drift, and then as they get caught up in the westerlies, they tend to recurve and die out as they go over the colder ocean water farther to the north. A lot more there in the Pacific, and then there's these are the tracks in the southern hemisphere. These are the genesis events measured between 71 and 2001. Every point indicates a genesis event, so you can see that they basically they don't form on the equator. There's no Coriolis force on the equator. They need to have some Coriolis force, and so they'll form off the equator, and that's where they mainly live. Okay, annual cycle. This graph shows the average number of tropical cyclones per month in the northern and southern hemispheres. Hurricanes tend to follow the sun, peaking in the summer and autumn, but all but vanishing during the early spring. Typhoons can develop over the west and north Pacific during any month of the year, but they are rare in winter. Okay, so here is again with the a couple of different. They have a tremendous variation in size. So this Hurricane Floyd again somehow visualized, so you could rendered so you could see the spiral rain bands beneath the cirrus and the cirrus anvil shield. And here's Hurricane Andrew, much smaller. These are from pre-satellite days pre-satellite days. This is Camille. I think it hit around Louisiana, the coast of Louisiana. A lot of damage. And then a much bigger one here, Hurricane Faith in 1966. Here are some records. The largest ever is Typhoon Tip. They're called typhoons in the Pacific. Typhoon Tip was 1,200 miles across, and I think they measure that by the 2 meter per second contour. Yes. No, just the name, just tradition. And hurricane, and in Australia, they're Willy Willies. So then here's another one, this Hurricane Ike, and this is the largest of the Atlantic. They tend to be bigger and stronger in the Pacific. Here's the smallest ever, Tropical Storm Marco, 10 miles across. Climatology. This is I think this is satellite-derived winds from Chris Belden and what velocities painted on. This is a log normal distribution of the outer radius. So the typical radius is about 420 kilometers, the median radius. And so to give you an idea of their size, basically 1,000 kilometers, like this, and in the median. But they can get very large, as you see, or very small, over here. Yeah, in terms of annual TC count, there's a seemingly a statistically steady number of about 90 per year globally. Nobody knows why. It's one of these things people are working on. Why are there 90? Why is the sky blue? It's one of those questions. Why are there only 90 per year? A little bit about trends, because I know I saw a few of the talks had to do with climate change. Here is a graph of the distance from the equator which tropical cyclones reach maximum intensity. So in the northern hemisphere, they seem to be creeping further north when they hit their maximum intensity, and the same goes for the southern hemisphere. And this is the last slide I have from this talk. The second talk's a lot longer, so. Anyway, so the time series. This is the time series of satellite-derived proportion of major hurricane fixes. Fixes, they fix the position and intensity at a certain place. It shows that the fractional proportion of global major hurricanes to all hurricanes has gone up in the last few decades. And this is from a paper by Paul Cosin et al. In the Proceedings of the National Academy, 2020. And at that point, I'm going to finish this. This is what I have on the structure and basically what a hurricane is. We could either stop now and go into it. Take a few minutes, or do you want to? Maybe I should continue a little bit. I'll give you the first part of the next lecture because it kind of goes right. It's kind of contiguous to this. So let me bring up the. That one. Yeah. Okay. Now you'll have copies of all this, so you can go back and pore over it in your leisure. Let's see, where is it? Slideshow. There we go. Okay, so this lecture is divided in two pieces, and I think we'll stop after the first piece and take a break and then come back to the second piece. The first piece is on the statistically steady state axisymmetric tropical cyclones. And we'll start out with taking a look at this tangential wind distribution and putting that together with the temperature perturbations. Again, I just explained this is the thermal wind relationship. Tangential wind decreasing with height and temperature perturbation decreasing with radius away from the center. Okay, so I'm going to write down the equations as they that pertain to this kind of hurricane. It's basically a circular flow, so cylindrical coordinates are the most convenient for solving equations related to the hurricane. And most of these are meteorological variables. Temperature T, using the standard definitions. Pressure P. Pi may be a little bit unfamiliar. It's the Exner function. It's the normalized pressure. This kappa is the gas constant divided by the specific heat at constant pressure. What else? QV is the water vapor mixing ratio. Theta V is the virtual. As the state E is the equivalent potential temperature. And just for the purposes of this lecture, you can think of it as the sum of potential temperature and this quantity here, which represents the and the release of latent heat. It's L times QV divided by Cp times pi, and L is the latent heat of vaporization. So this next slide may cause you to go running from the room, but it's basically the complete equations that will describe a system like systems we're going to be talking about. So in polar coordinates, and there's a nice review article here up by Montgomery and Smith in the Annual Review of Fluid Mechanics. And this is the equation for the radial momentum. I showed you the radial flows into the storm. This is for this one here, the tangential wind equation. It governs the circular flow. The vertical wind equation. This is the conservation of mass. And this is the first law of thermodynamics written in terms of the potential temperature. And definitions of density in terms of these variables are given down below. Here's pi again and kappa. Now, these are the equations that fluid dynamicists use, but meteorologists don't usually think, don't measure density. They measure temperature and pressure. So the more convenient variables are to use those variables. So first, so almost everything I have to say here is going to be based on an approximation to these equations given by the underlying equation. So happily, once you make those approximations, most of these equations disappear. And so so you're imagining then a flow where the U and where the flow is just swirling round and round, so it only has a V component, and U and W are 0. Even though I showed you that there's U and B and W, but you can imagine the stationary state, and the state, the stationary state, statistically steady state, where the radial wind equation reduces the gradient wind balance, where the pressure gradient balances basically the centrifugal force per unit mass and the Coriolis force per unit mass. And the vertical equation is basically the hydrostatic equation. So if we transform these equations in terms of P and rho into theta and pi, we get something a little more familiar to meteorologists. And so the step here that I'd like you to try, you can try this at home. You can take the vertical derivative of the radial equation and the radial derivative of the hydrostatic equation, and take the difference between those two, and you get this equation here. And these terms involving the Coriolis force are small, and well, in fact, this is small. This whole term is small, actually. And you get this. This is basically the thermal wind equation in cylindrical coordinates. And it tells you, yes, when V squared decreases with height, you should expect that the temperature perturbation should decrease with radius. Right? So negative, negative. Right? All right, so I'm going to take this a step further. So you take that equation, suppose you just integrate around the box. Okay, so we just integrate, so this is basically the centrifugal force. So if you integrate this from top to bottom, assume that V vanishes at the top, gets very small. So you can integrate this, and then integrating this in radius leaves this radial integral of V at the bottom, equaling the integral over H of the temperature on the axis as compared to, on the axis at a certain level as compared to that same level as compared to the temperature far away. So that would be the theta primed. It's defined down here. So if you assume a Rankine vortex, and you can do this integral exactly, and what you get then is that the V squared at the bottom is equal to the vertical integral of the buoyancy. So the flow going round and round and round is basically corresponds to low pressure at the ground, and that low pressure at the ground must be balanced by must be produced by warm air on the column. You don't have to assume a Rankine vortex. Any vortex will do. It'll just produce a different coefficient. Instead of 1, it would be something else, some order 1 quantity. So in terms of physics, what does it look like? So what I'm imagining is that we have a situation where a ball that's constrained to be on a plane, circling round and round and round, and there's a centrifugal force per unit mass that's acting on it, making it, trying to fling it outward. And the ball is connected by a string that comes up through a slot, and this is the force needed to keep the flow in equilibrium, and that force is the buoyancy force. So it's just a very that's the way I like to think about it. The V at the bottom's going round and round and round. It's a centrifugal force, and it has to be held in order that it doesn't fling away by the buoyancy force in the middle that's pulling in on it. It's very fundamental. So what does equivalent potential temperature and angular momentum have to do with this? So as we showed in the first lecture, if we use this definition of equivalent potential temperature, we see that what's happening here is as the air comes in, it's increasing its equivalent potential temperature. And that's basically two effects. The temperature at the EC surface is almost constant. So as you go to lower pressure, there has to be a sensible heat flux from the ocean to the air, because T has to be constant. Theta is equal to T times P reference divided by P to the kappa. So if T is constant and P goes down, then theta goes up. Okay, so there must be a sensible heat flux. But more important than that is there's a flux of moisture into the air parcel swirling and coming in like this. So that's why theta E is increasing as you go in. This observational fact about hurricanes was known. The fact that theta E increases dramatically as you go towards the center was known as far back as the 1940s. But then on its journey inward, it then goes up. And as it goes up, if you remember, the pictures of the vertical stadium walls in the rain field, it's losing all its rain. And if it loses all its rain, this term goes away. And so that means for theta E to be conserved, theta has to go up. So that's basically the basic source of warming is through the conservation of theta E, where all that vapor that's been acquired has now been converted, that it rains out and releases latent heat, and that heat goes into the swirling vortex, and that's what makes the core warm. And and that's accompanied by this the air coming in, losing angular momentum, but then conserving as we go out. As I said, this was known going back at least 70 years. This is the original paper on this is in German. I put it here for those of you who read German. It's by Ernst Kleinschmidt, and it was reviewed in the compendium article by Eliasson and Kleinschmidt, a very famous book in its time. And they said, they basically understood the basic workings of the axisymmetric steady-state hurricane, where air parcels, as they come spiraling in from 1 to 2, they pick up their moist entropy, or theta E. I'm going to use those terms interchangeably. S is the moist entropy, and theta E is the equivalent potential temperature, but they're related through a simple algebraic formula. So in going from 1 to 2, moist entropy increases. It loses angular momentum to the surface, but not so much that it can spin faster. So whatever's left is spinning fast. It conserves more than it loses, so that the air spins fast as it gets to the center. From 2 to 3, both S and M are conserved, and from this you could construct They didn't do it at the time, but it was done later by Kerry Emanuel, a theory for the shape of these surfaces and the wind speed. And if you want to know, they were kind of vague about what happens from 3 to 1, and unfortunately Raphael just left, so I was going to tell you to go see Raphael on this. We wrote a paper. He was a visitor one summer, and we wrote a paper on this, what things that could be happening in bringing the air back to its thermodynamic state that it started with. For this to be a steady cycle, the air, however it gets back there, whether it descends directly or whether it comes from someplace else, has to be thermodynamically as the same theta E, because otherwise it can't be a steady state. Okay, so let's now work with these equations. This was, the problem was basically solved some 30 years after the Eliason and Kleinschmidt article, and this is a paper by Kerry Emanuel, very well known now, 1986 paper on the steady state axisymmetric inviscid in the interior flow using just the gradient wind and the hydrostatic equation. And what I've done here is now transformed to radius and pi coordinates, pressure coordinates, and it makes some things work more easily. So anyway, so you do the same sort of operation. You take the vertical derivative of the gradient wind and subtract the radial derivative of the hydrostatic equation. And you're assuming you assume that we're at saturation. So all the air coming up is saturated. And if that's the case, then theta is a state variable. It's a function of pi and s. So when you take this equation, the vertical derivative with respect to pi, this term goes away, and then take the radial derivative of this equation here. It becomes, you get the gradient wind equation that looks like this, but using the fact that theta is a function of pi and s, I can rewrite this as Cp d theta ds at constant pi using the chain rule times the SDR at constant pi. A critical step, which I'll do in the next slide, is replacing this term here, d theta ds at constant pi, with dt d pi at constant s. And that allows the gradient wind law to be written like this. And this allows this equation simply to be integrated along, upward in pi, and as a function of pi and radius. So let me just, I'll just show you the Maxwell relationship. This is how you get it. You write down the first law of thermodynamics, you write down definition of enthalpy, and take the partial derivatives holding quantities constant, cross derivatives, and gives you that relationship. It's in the appendix of the manual. Anyway, so starting from that equation, that is the thermal wind equation, you have then 1 of r squared times dm squared, d pi is like a vertical derivative. Remember we did for the thermal wind equation, equaling the minus dt d pi times the SDR. So in order to close this system, you need to have S as a function of M. What Kerry Emanuel did is he assumed that S and M are, along an entropy surface, along an angular momentum surface, the entropy is well mixed. So therefore S would be a function of M. In the reasoning of Eliason and Kleinschmidt, they said, well, it's conserved. If S is a conserved quantity and M is a conserved quantity, then they're functions of each other. So when they come out of the boundary layer, parcel comes out of the boundary layer, and it has a certain S that it acquired as the air flowed in, and a certain M that it has. It's the parcel conserves that S and M, and therefore and they're functions of each other. So so using that, I like to think of it that way. Using that, then you can express the SDR as the SDM times the MDR. So now what you have then is that the SDM, that's a constant, it's independent of pi, and M, which is also, if you're on a certain M surface, then these M and the SDM, they're constant. So now you can integrate this equation in pi and get the shape. You get r squared, then the radius of that M surface as a function of temperature. And here's what it looks like. So this is a very famous equation in the business, is that the radius of a particular M, these are M surfaces in the cartoon, and it's the r squared is equal to m divided by the SDM. These are both in principle known as you come out of the boundary layer, and they're constants, are proportional to, r squared is proportional to T minus the outflow temperature. So you can see say at the height of the boundary layer, T is equal to T something, and you'll get the radius knowing these quantities. And as T goes to T out, R goes to infinity. So these M surfaces are going up and sloping out. Think about the football stadium that I showed you in the earlier pictures from inside the tropical cyclone. Okay, so how do you determine then this DSDM? What's done is a simple slab boundary layer model is developed. And so in that slab boundary layer model, you could write an equation for M, the angular momentum. Here's losing angular momentum. There's a sink term here. And then an equation for S, where S sub S is the saturation entropy at the sea surface. So this basically is increasing the entropy as you come in, and this is basically decreasing the momentum. And what you could do is combine these equations, and you can see now you no longer need to know U, because you can eliminate U from the two equations, and get an equation for this DSDM in terms of the drag coefficients CD, the heat transfer coefficient CK, and these quantities. The difference, the disequilibrium between the entropy in the boundary layer and the sea surface entropy, and the angular momentum minus 1/2 FR squared in the denominator. So if you combine these two equations, neglect this term, I'm depending on you to go back and look at this stuff, because this is like, it took me a long time to understand what's going on here. Anyway, so you and you get this formula of potential intensity. So this gives you the maximum wind speed, maximum tangential wind in a hurricane, as a function of these CK over CD, which is the ratio of heat transfer to drag. This is this equilibrium. S delta would be the entropy in the boundary layer minus the difference between the saturation entropy at the sea surface. So basically, if you have the sea surface temperature at say 27 degrees Celsius, calculate the saturation mixing ratio, and you can calculate the saturation entropy. And then whatever S sub delta is represents a disequilibrium between those two. So you're getting entropy fluxed in, and then the difference in temperature between the temperature here and the outflow temperature. So as it work, this is the potential intensity for in a worldwide map. You can compute these things from data, and which made it very powerful. And potential intensity basically follows the tropical belt here. You'll notice that it's highest at the equator, but and this formula doesn't involve F, so it doesn't know about F. It's not directly, and so without something to seed, to trigger the disturbance to start it, you won't get even though it's potential intensity. This is saying this is the highest speed it could reach. Doesn't mean it's going to reach that speed, but it's the highest speed it could reach. And apparently along the equator, that it actually reaches zero, although it could, if the atmosphere put something spinning there, it could reach this intensity, but there's no rotation at the equator. So more on the steady state TC structure. We have a kind of a table in this recent paper looking at sort of historical developments of this steady state model, and some of the uncertainties that go in here. Well, this theory set off a kind of reinvigorated the whole air-sea interaction problem, and people went off in search of CK and CD, and as you can see from these studies here, there's a lot of uncertainty at high winds. These numbers are known fairly well. Low wind speeds, but high wind speeds, the ocean surface is turbulent, it's spray, there's big waves, and so it's easier to write these equations down than there is to actually get a solid measurement on CK and CD. Other uncertainties is that the ocean feeds back. As a hurricane comes through, it deepens the mixed layer and causes a mixing of cold water from below into the ocean mixed layer, and that tends to damp any hurricane that comes in its wake. And finally, the effect of supergradient winds. I've made it, that this whole theory is predicated on the gradient wind approximation, and there's been a number of works on the effects of supergradient winds. So I'm going to end at this point in the lecture. This is the end of the part on steady state theory. We basically went through the series of approximations needed to derive the manual potential intensity, and you come up with a picture with this art, basically that these surfaces have a very definite kind of curve in temperature radius space, and the dependencies here in terms of moist entropy and the temperature difference between the source and the outflow. Okay, so we'll end here. We'll take a break here, and then we'll go into evolution. I mean, how does the hurricane spin up? Okay, I'll take questions, or we can. Yeah, go ahead.
So about the size of the eye, you mentioned 50 kilometers. Is that like the relation between the size of the hurricane and the size of the eye, or is that constant?
I think that, yeah, they kind of scale together. My experience. I can't put my finger on the data point, but yeah, I mean, some hurricanes have very small eyes. Some have big eyes.
Regarding the sources of moisture when you showed the cycles, how local is the source of moisture for tropical cycles? Because for instance, in latitude cycles, the source of moisture could be even 2,000 kilometers away.
In principle, it's very local, because it is any. I think I'm going to cover this in the second part here. But like if you're thinking in terms of a cumulonimbus cloud, there's so much moisture that will get invected in and be consumed by the cloud. But you can't sustain a hurricane that way, because you have to. Well, a couple of reasons why. One of which I'll talk about here, but simply the advection dynamics of bringing in moist air won't work out. So it's mainly the fluxes from the sea surface that's supplying the moisture. Like the diagram on theta E. Yeah. So theta E. That's not, the high theta E air is not coming from someplace else. It's being created in situ by the fluxes off the sea surface. And high theta E is what you need to get the warming that's a central feature of the hurricane, the eye wall warming. Yeah. No, it's good. People have argued about that for generations, and but I think everybody agrees upon this now that. Yeah, it can't be sustained by just convergence over a large area. It doesn't change the theta E, 1. Anyone else? I don't think there's coffee, is there? No. Okay, well, why don't we come back at 5:30? I think I only have about a half an hour left, so. Okay, at 5:30. It's 5:20 now. Okay, we all in? Okay, so back in 1985, I back in 1985, I taught a graduate course at MIT, and the way it works there is that the students come in, and and then if they like what they hear, they come back. So I started out with 12 students, and next time there was 9. Next time, it finally leveled off at 6. So I was expecting to be fewer people this time. Thanks for coming back. Okay, I make that one. Okay, evolution. So we go back to our cartoon where we integrated over the box, and we found that the maximum tangential wind is proportional to the integral of the buoyancy over the center axis. So if we go back to our cartoon, our balanced cartoon, with the ball on a string rotating around, what we want to do now is ask, well, how can we increase the circulation? How can we increase the velocity v? And so if we now introduce the concept of the conservation of angular momentum, then the v is related to r times v is basically a constant. The ice skater bringing the arms in spins faster. So I can write the centrifugal force per unit mass then as this function, gamma squared over r cubed, where gamma is the angular momentum of the ball, and plug it in here, and we could solve then the force balance for r cubed, and that tells you directly that if you want to decrease the radius, if you want to decrease the radius and therefore have a larger v, then you have to have a stronger f. F gets bigger, r gets smaller, v gets bigger. Conserve angular momentum. All right, how do you do that? So now thinking about evolution, and we'll stay within the confines of an axisymmetric formula for now. So if we have this radial vertical plane, there's a number of ways you can make the angular momentum come in, and therefore angular momentum is conserved, the radius decreases, and the spin increases. So there are two routes in here. The one that I talked about earlier was the radial velocity coming in through the boundary layer, by the Ekman effect, and I'll talk about that in a minute. And one is just due to cumulus convection in the early stages of a tropical cyclone, drawing air in. I think it relates to a question that was asked about how far you can go with just cumulus convection. So let's talk about the Ekman effect. I think this is one of the more fascinating effects in rotating fluid dynamics. And there's a very old film library that you can access if you're interested in fluid dynamics. And this is made at MIT in the early, I think it was in 1960. And if you go through the library, you probably never stop at this one because it's called secondary flow. And what's that got to do with rotating fluids? Anyway, secondary flow is the title of this little movie, and it shows a professor in his laboratory, and he's and he's asking about does the bathtub vortex. Now, most of you are probably familiar with the bathtub vortex. You still take baths every now and again. Most of you take baths, I think. Maybe. Nah. Anyway, next time you take a bath, you'll see a rotating flow, and the surface is dipping down. Think of this like the surface dipping down is like the tropopause coming down in our tropical cyclone that's causing the warming. The surface dipping down is because you have low pressure in the center, and it has to be balanced hydrostatically, and the way to do that is reduce the height of the column. So that's what this is. So the professor, he asks, how does the water exit the bathtub? And he takes a dye, he injects dye at the surface, and what you see is that the dye goes round and round and round. It doesn't seem to go out very, very quickly. And then he goes successively lower positions with the dye. He finally gets down to the surface and lets the dye go and right down the drain. And that's the effect of the Ekman layer. And I'll explain that. So in a rotating fluid, the simplest possible, we have a balance between the radial pressure gradient and the centrifugal force. The radial pressure gradient is inward, and the centrifugal force is outward. Let's do a thought experiment. Suppose we put a no-slip condition or friction condition at the surface, just above the surface. The pressure gradient doesn't change. Just as the classic boundary layer approximation is that through the thin boundary layer, it has the same pressure gradient as you go through to the ground. It has the same pressure gradient, but it no longer has the centrifugal force because you've got you set it to zero basically at the surface. So without the centrifugal force, it drives the flow in. The pressure gradient drives the flow in. So yeah, so that's basically in a nutshell the Ekman effect. So so this is one of the things I'd like to note about how tropical cyclones can intensify. I want to, before we leave here, draw your attention to these little arrows here, because as the flow evolves, it's a rotating this rotatium stadia. Is that the stadium walls retain that image from the aircraft reconnaissance flights. You have this rotating flow that's decreasing with height and kind of spins outward, and it has this warm center because as the flow evolves, the flow in the middle is coming down and warming the air because it's taking all the stably stratified air in the atmosphere, compressing it and causing that temperature perturbation. So at the steady state, it's no longer moving, so you no longer have a vertical velocity, but it had to have existed to produce that downward motion that's there in the steady state. Sure. I'm sorry, could you repeat the question?
Yeah. This effect of the on the rate. So the most together, but different what the center is right above the
Right above the ocean.
Is this mirror like below the surface? So most of the that gets
No, no, I'm talking about above the surface of the ocean.
but it's not mirror below.
Yeah, the ocean current may be moving, but it's not critical. I mean, the air is moving at maybe 50, 60 meters per second inward. Okay, there's been a lot of theorizing about the effects of the cumulus convection in the early stages, and where you have a number of what they call rotating vortex hot towers, and that's also covered in this review article here. Yeah. So and you can basically add them up by Stokes' theorem here. The circulation around the whole thing is the sum of the circulations within each rotating tower. Here's a little movie supplied to me by Roger Smith. I did this little simulation just to give you an idea of what you're looking at is the isocontours of vertical velocity, showing the rain bands and then the center forming and becoming stronger and eventually dominating the flow in the tropical cyclone. So I show you that to acknowledge that yeah, it's complicated. It's not axisymmetric, and yeah, so it's interesting to look at these kind of movies, et cetera, et cetera. But at the end of the day, we still have our basic equation. So now we integrate around, as well as integrating around the radius and height, we integrate around azimuth. And you still have to satisfy an equation like this, and in order to have a V and to have a strongly circulating V, you have to somehow increase the temperature perturbation, just like I showed in the simple example with the ball on a string. So that's why this figure is so important, because the flow that's coming in and picking up equivalent potential temperature and then conserving it. Remember, all the rain is falling out by this point, so this term is going to zero as you get to the top here, and that's in order to conserve theta E at this same value, theta has to go up. And that's the basic source of the warm air in the center core is this is the conversion from latent heat, and so how we covered that before. But in order to increase theta, you have to increase theta E. So that's why just a cumulus convection model, it takes the air that's there, has theta E, and will convert it, but that's all you get. That's all you get. I mean, if it causes rotation, and the rotation, and there's more advection of the same air, has the same theta E, you won't get any warmer in the center. Let me just show a little example of what I'm talking about here. Here's a cumulus cloud, and yeah, you get so much temperature drop, but temperature increase. But eventually you get rain, and temperature and the pressure goes up. So it really doesn't contribute to lowering the pressure in any net sense in a tropical storm. So two things have to happen. You have to have saturated air, so that you don't get these cold downdrafts. And the other thing is that so when this cloud goes up, it may follow a where is it? There we go. It follows a moist. Oops. Oh, here we go. Follows the moist adiabat, and you get so much temperature increase. Okay, but to increase theta E, so that's a fixed theta E, but to increase theta E with the temperature in the boundary layer being constant, remember the temperature in the air that's in contact with the ocean is basically got the ocean temperature, so it's staying constant. So how do you increase theta E for successive parcels of air that are coming in and going up? And there's a couple of ways to do that. So one way to do that is just to increase the QB in the boundary layer, and that will basically give you a higher moist adiabat, a larger moist adiabat. It'll increase the theta E, so when that parcel rises up, it'll be somewhat warmer. The other way to do that is to go at lower pressure, at constant temperature. The surface points then move up, and that moves the curve even farther to the right, the theta E curve. So some process like this is needed in order to intensify the tropical cyclone. So all the convection, it's nice and everything, but it doesn't the really important interaction is between the developing cyclone and the sea surface that increases the theta E, which allows the cyclone strength to increase. Because without that increasing theta E, you don't get the increasing temperature on the axis, which is needed for thermal wind balance. So the only way to increase theta E is through the surface flux, and so that's illustrated here. So I'm going to show this is something that those of you who wind up working with the data set that I provide. This is a data set that this simulation was reported in this paper. It's Peng, Rituno, Bryan, and Fung in Journal of Atmospheric Sciences. And we looked at the evolution of the M surfaces and the theta E surfaces as a function of time, starting from a sort of a plain vanilla type vortex. So this is the angular momentum in color. So starting from an initial vortex with almost zero gradient of what's contoured here is moist entropy, S, Cp ln theta E. And what you see happening here is like this is the and this is an axisymmetric model. And so as the flow transfers, this is the angular momentum. So there's a vortex here, and that vortex then is allowing fluxes of theta E or entropy from the sea surface, and you can see those lines rising up out of the sea surface of higher theta E. And what happens over time is that they give rise to convection. And this is sort of the initial phase where you're creating moist convection. And these, when I say convection, it's not like it's the axisymmetric version of the convection. It's not the actual 3D cells. It's rings of convection, but they have the same net effect. And this sequence is showing how the angular momentum is moving in a series of stages. It's being you have the Ekman effect bringing higher angular momentum in, convection bringing the higher momentum air upward, and at the same time bringing higher entropy air upward. And it continues in that way until we get to the what I call the Emmanuel state, where the S surfaces given by the contours and the M surfaces given by the colors come into alignment. And once they do, then we can intensify the vortex according to Emmanuel's theory. This is just to illustrate some of the points here. This is theta prime is given by the white contours, and showing the evolution of theta prime as theta E is increasing. This is theta E, and B max is down below here. So I'll start again. So this is in this state where it's now reached the Emmanuel state, where the S and the M surfaces are congruent. And we have here V is 55 meters per second, and it's on its way up. Theta is 15 degrees at the center. Now V is 80 meters per second in the simulation, and theta is at 25 here in the middle. And the color field in the background is theta E, and this is gradually increasing, as it should be, and finally it reaches rather large values of theta E. The blue is up to about 360 in the boundary layer, going up through here, and it reaches a maximum of 90 meters per second with theta prime at 35. So this is that simple cartoon of V increases, theta prime in the middle increases, and that happens through the agency of increasing theta E as the cyclone evolves. So This theory, is not without controversy. There's you'll find discussions in the literature whether or not the Wishy effect is really needed, and there's this nice exchange here in the literature you'll find between these groups here. Basically, it comes down to whether or not the increases in V are necessary in order to increase the ADE, and there's some interesting discussion there. But I think the bottom line here is that convection by itself, as I said several times, doesn't intensify tropical cyclone. You need something to increase the ADE, and that's the only place to do that is through the sea surface. So that's the essence of the Wishy theory, and yeah. So there's the summary slide for intensification. Is that here's our thermal wind relationship, but integrated. So we have the maximum wind in terms of the integrated buoyancy on the column, on the center column. If we take a time derivative of that, then it shows that to increase V, you have to increase the buoyancy on the column, which means you got to increase theta. And the only way to do that is to increase theta E. So it's connected there. So anyway, that's basically the bottom line. For me, you may see a lot of papers on convection, exotic effects, but if you keep your eye on the bottom line is that theta E's got to increase in order to get theta increase to satisfy thermal wind for increasing vortex. Anyway, there's a lot more to be said about this, but this is what you can do in maybe 2 hours, and yeah, we could talk about it. Anyway, that's it. What's the best way to do it? Maybe I'll pull this up. Hold on. And no, maybe this smaller. Yeah. Anything through the lecture here? Okay.
Can you again show how we get to the thermal wind balance on the bicycle? I think it's 11, slide 11.
Slide 11?
Or is it, no, the one below. The one below. Yeah.
That one? Okay. This one. That one? Oh, the earlier one.
Yeah.
Yes, I did this one just because it's familiar. It's radial and vertical, and I think everybody can think in terms of geometric coordinates, radial and vertical. But you have to approximate to get the simple formula. In the formulation of the more precise theory. More precise theory, we transform from vertical coordinates to pressure coordinates. So these are the same two equations, gradient wind and hydrostatic, but in pressure coordinates, radial pressure coordinates. And then from there you can do exact manipulations. Okay, well, anything occurs to you, come see me. I'll be around. All right, thank you.